Good afternoon, everyone. This will be our second recitation session for this class since we started this online domain. All right. We're gonna solve a bunch of problems during this session, and mostly they're gonna be problems about polarization, right? So permittivity, dielectric materials. So those are the topics that we covered recently. I want to start with example 4.15 from the textbook, which states that you have, it's a problem that about a coaxial cable. Coaxial cable. What's a coaxial cable? Coaxial cable is typically two concentric let me draw it this way. So there is a cylindrical shell conductor. So this is a conductor, inner cylindrical conductor shell, right? And let me draw the outer shell. The outer shell is like that, right? It could be any length. And then in the middle, there is some dielectric material, right? So some dielectric material with a certain epsilon is sandwiched between those conductors. All right. So, all right. And the question is as following: assume. So let me do like a cross section. So this is going to be a cross section. So I'm going to take a cross section of the coaxial cable, and it's going to look like this. So I have the inner core, the inner shell, right, cylindrical shell, and the outer cylindrical shell. The inner has a radius of A, the outer has a radius of B, and then there's the material sandwiched between the two shells. And those are two conducting shells, right? So the problem states that, hey, we know that in the inner shell, we have a certain plus Q charge, positive charge, capital Q, per meter, right? Every 1 meter, which is the unit length in this case, we have plus Q charge distributed over the whole surface of the conductor. The problem statement asks you to do two things. Find the magnitude and direction of the polarization vector inside the dielectric, essentially P inside the dielectric. How are the dipole densities polarized inside this dielectric, which is P, right? The polarization volume charge density in the dielectric. Due to this polarization, what rho PV will manifest inside the dielectric? What volume charge density would appear inside the dielectric? And then the surface charge densities on the surfaces of the dielectric, right? On surfaces of dielectric. There are two surfaces in this case. There's the inner cylinder and then the outer cylinder. Okay, so right. So we want to start solving this problem, and to start, and we know, of course, the material is epsilon, right? So to start knowing epsilon, I mean, what does epsilon give us? Epsilon gives us the relationship between the flux density. This is the epsilon, the permittivity of the material. Always gives us the relationship between the flux density and the electric field intensity, right? And we said the flux density is the total polarization, the polarization of free space plus the polarization due to the material, right? This is how we are interpreting the flux density vector, right? So another relationship we know is that D equals epsilon naught E plus P, right? So this gives us the way to calculating P. So now that we know that P is going to be equal to D minus epsilon naught E, right? Once we know D and we know E, we can calculate P using this expression. How do we find D and E? From Gauss's law, right? So we know the fundamental axiom, which is that divergence D is rho, right? I can write it in two ways, or divergence E equals rho over epsilon, right? So now because we have a material, it becomes epsilon, not epsilon naught. Okay, and recall that D equals epsilon E, right, inside the material, right? So we can use Gauss's law to find the field E and D inside the material. In this case, let me redraw. We have to find the Gaussian surface, right? The Gaussian surface, right? So I'm gonna use the integral form. So this is the differential form. I'm gonna use the integral form, and to do that, I need to find the surface. The surface is gonna be, this is A, this is B. The Gaussian surface is gonna be some cylinder inside the material, right? And then this extends, right? This is a cylinder, right? For a unit length. So, and then so this extends, right? And then the cylinder ends later, right? But then the caps, because of the symmetry, the field is always gonna be in this direction, whether it's E or D, pointing out, right? So, and the field will always be embedded in the caps of the cylinder. So the dot product will be 0 and will be 90 degrees or in the same direction as the surface on the cylinder itself. So the dot product will give us the magnitude of the field. Right? So applying Gauss's law, the area on the body of the cylinder is 2 pi r. This is distance r, small r, cylindrical coordinates. 2 pi r d, sorry, 2 pi r L, which is the length we are interested in, the length of the coaxial cable. Right? So this gives me the area times the magnitude of D equals what? The total charge, right? We said right. So we said Q, right? The total charge is Q per unit length. Let me say that Q per unit length. How much length do we have? We have L length, right? So what's the total charge? The total charge is Q per L. If L is unity, then we get a total charge of Q. If L is double unity, we get 2Q, and so on and so forth. Okay, so this is Gauss's law to find D, right? So D in this case is going to be, L cancels with L, D is going to be Q, the magnitude of D, of course, is going to be Q over 2 pi R, or R small. What about E? Well, we said that E is going to be D over epsilon, right? So E, remember this equation? So E is going to be, once we found D, we found E, right, in the material. So it's going to be E over 2 pi epsilon R. Right? And again, I mean, from the Gaussian formalism, although we lost the vectorial information, from the symmetry of the Gaussian surface, we can put it back in. So I can say in cylindrical coordinates, d as a vector is just going to be r small hat q over 2 pi r, and e is going to be r small hat q over 2 pi epsilon naught r. And we're set to find p. So p is, oh, I wrote it down here. So we're going to use this equation, right? P equals d minus epsilon naught e. That's what p is. P equals d minus epsilon naught e equals, I'll write it down and then manipulate it, right? Minus epsilon naught take everything common out, so I have r hat q over 2 pi r 1 minus epsilon naught over epsilon, and this will be p. This is the polarization vector, right? So in Coulomb per meter squared. So that covers part A of that problem, finding the polarization within the material. The next part of the problem is finding the volume charge densities and the surface charge densities in the material due to the polarization. Right, starting with part B, so we know the equation, right? Rho PV, we derived this in the last lecture, is minus the divergence of P, right? And then the divergence of P, divergence in cylindrical coordinates, it's some, it is, 1 over R d R AR over dr small, right, plus some term that is the derivative of with respect to theta, sorry, phi, and some term that's the derivative with respect to z, right? But those terms will cancel out, will be zero. Why? Because as you notice here, p has no is not dependent on theta or on phi or z, right? So we don't need to care about those terms. We can find the divergence directly. So this is going to be minus 1 over r d r q over 2 pi r 1 minus epsilon naught over epsilon over dr, right? This interesting thing. And notice r cancels with r here, and we end up with an expression inside the differentiation that is not a, oh, this is epsilon naught over epsilon, sorry, epsilon naught over epsilon, right? We end up with an expression here that's not a function of r anymore, so this whole thing becomes zero. So rho PV is zero, right? So there is no volume charge density that appears due to the polarization, right? Now part C, what about the surface charge density? Where is the surface in this problem? When I say surface, by the way, I don't mean the surface of the conductor. I mean the surface of the boundaries of the dielectric. The boundaries of the dielectric in this point are the boundaries that just touch the inner conductor and touch the outer conductor. So those are the boundaries. And we can use the second equation that we derived last lecture, which is what? Which is rho PS, right? Oh, yeah, so there are two surface charge densities. There's the one at distance A and the one at distance B, like we said, right? So so the first one at surface A is going to be P at A dot N, right? N hat. What is N hat? N hat is the unit vector coming out of the inner boundary, in this direction, and then rho PS at B is the outer shell, right? It's going to be n hat is going to be this vector. So this is n hat. Right? It's going to be coming out of the outer boundary. Right? So all we need to do is we need to know P at those boundaries, right? So P, what is the equation for P? P looks like this, right? It's pointing outwards. You know, P is always pointing outwards, right? In the material like that, right? So that means P is going to be 180 degrees with respect to N at the inner boundary. That's why we're going to get like a negative sign, right? So let me do the inner boundary first. So PA is going to be this equation, right? Q over 2 pi R. So it's going to be R. I'll write PA first. Q over 2 pi R. What's R in this case? R is in this case is A, right? Right? And then 1 minus epsilon naught over epsilon. Right? And for the inner boundary, N is going to be minus R hat. Notice because N hat is pointing inwards, right? Because the boundary is inside, right? The boundary of the dielectric, the normal vector coming out of the dielectric inner surface is pointing inwards, right? So all I have to do is do this thing. I end up with minus Q over 2 pi A 1 minus epsilon naught over epsilon coulomb per meter squared. So this is the surface charge density at the inner boundary of the dielectric. The surface charge density at the outer boundary of the electric is going to be P dot n hat. In this case, n hat is going to be R hat. This is n hat here, right? It's going to be R hat. So this is going to be, this is P at B. So this is going to be, again, this is going to be R Q over 2 pi B 1 minus, can I make this mistake? It's epsilon naught over epsilon. Epsilon naught over epsilon naught is 1. So, all right. So 1 minus epsilon naught over epsilon dot R. So the surface charge density due to polarization at the surface of the dielectric touching the outer conductor is going to be rho PSB equals Q over 2 pi B 1 minus epsilon naught over epsilon coulomb per meter squared. Yeah, and that concludes this problem. Okay, next let's go through example 4.16. This is an example about dielectric strength. Right, so yeah, it's about dielectric strength and breakdown in semiconductor devices. Right. Now, I mean, we covered dielectric materials, but semiconductor devices it's not accurate exactly to call them dielectric. They have dielectric properties, right? So they are somewhere in between. So we have conductors with their concentration of free charges that are free to move anywhere, right? And then we have dielectric materials with their bound dipoles or a polarization vectors. Right? Their concentration of bound dipole densities that react to the electric field. Right? But semiconductors are really somewhere in between. Under some conditions, they act like conductors. Under other conditions, they act like dielectrics. Right? We are, in this example, we are concerned with their properties as dielectrics, with their capability of providing insulation. Right, so in semiconductor design, you would have like a substrate with a semiconductor material, right? And then you could have like some copper traces and whatnot, right? And the semiconductor would sometimes act as a conductor, sometimes act as a dielectric or an insulator, right? And right. So one problem in semiconductor design is, what if you have two semiconductor layers, and then you need to provide insulation between them, right? So insulation is typically done by depositing a specific kind of special material called silicon oxide, SiO2. So this is the typical kind of insulator that we place between semiconductor materials, right? And it typically has a dielectric strength of 30,000 volt per millimeter. Right? Remember the dielectric strength for air? Dielectric strength for air was 30,000 volts per centimeter, right? Which gives me 3 million volts per meter. Right? So this is a kind of material that's 10 times stronger than air, okay? SiO2. So this example poses the following questions. So if we have two semiconductor strips, so this is strip 1 and strip 2, and we want to isolate them, right? And we know that within the constraints of our design, we know that the maximum voltage between those two strips is going to be 5 volts. What is the minimum width that is required to prevent breakdown in the insulation material, in the SiO2? Right? And we want to utilize like the smallest possible width, because as you know, in semiconductor design, the name of the game is making everything small. We want to compress everything into as small a volume as possible to get a dense design. That has been the evolution of semiconductor design since its onset. Right? So what is the smallest separation possible? Okay, so we've studied the electric field between two parallel plates that are like very almost infinite, right? And we know that the field is uniform. Right? For such a uniform field, we know that the voltage is going to be the field intensity times d, the distance, right? So right? And we know that this is the breakdown field intensity for this material. So I can go back and say d equals d minimum equals V is 5 volts in this case, over E breakdown. V is 5 volts, E breakdown is 30,000 volts per millimeter. Volt goes with volt. We end up, so millimeter, I do this calculation, I end up with 1.67 times 10 to the power minus 7 millimeter, which is, multiply that by 1 to the power 6, I get 0.167 micrometer. So this is the minimum distance. if I have two slabs, two traces, semiconductor traces, the minimum distance that is allowed before a voltage of 5 volts is going to break the material is 0.167 micrometers. I mean, this is pretty small. I mean, but you know, I mean, if you follow semiconductor design, especially microprocessor design, there are processes right now that are approaching 10 nanometers or smaller. I don't know what the smallest is right now, perhaps 7 nanometers, but definitely, I mean, current processes could go much smaller than this. So that tells me that for current processes, like 167 micrometer is 167 nanometers. This is 167 nanometer, right? This is huge compared to the processor. So that tells me in modern processes, the voltage inside the chip, so this is the chip, the voltages inside the chip between the semiconductor layers need to be way smaller than 5 volts. 5 volt is large, right? So that's one concern. So we found D min, which is 0.167 micrometers. That's one concern. There's another concern. Although 5 volts is the operational voltage, we need to design for higher voltages because there's a phenomena in semiconductor materials that's called ESD, electrostatic discharge. This is what happens when you walk on a carpet or wear like insulating shoes and walk for a while and then touch a metal door handle. You zap yourself, right? Or you handshake with a friend and you zap him and you zap yourself. So the same thing, I mean, happens. This is called electrostatic discharge. This also happens when you're handling semiconductor chips. Right. So electronic chips, what will happen is this buildup of charge can reach to voltages that are tens of thousands of volts in electrostatic discharge. Right. So that will zap any semiconductor, that will destroy any insulator. Right. So you have to kind of be mindful of that when you design those distances. You have to over design a bit. And that's also the reason why you have to properly ground your chips. And when you ship them, you notice that they are placed in protective packaging. So this is ESD packaging. So this is a special kind of plastic conductive packaging that allows the pins to discharge and no large ESD charge to accumulate that could kill those chips. And some chips have active limiting, like there is actual circuitry inside the chip that limits the effects of ESD. So just pure operational voltage is not the whole story for semiconductors. Okay, now this is part A of the problem. Part B of the example is as follows. So assuming the same conditions as A, what would be the largest potential difference allowable? Right. So I have the two slabs. What would be the largest, and this is the SiO2, what would be the largest operational voltage between those two traces, semiconductor traces? Well, we know V equals E break times D. We know what E break is. It's 3 times 10 to the power 7. Right, so it's 30,000 volts per millimeter. What is this per meter? Right, so this is 30,000 volts per, what's a millimeter? A millimeter is 1,000th of a meter, right? So it's 10 to the minus 3 meter. Right, so this is 1, 2, 3, 4, 5, 6, 7. This is 3 times 10 to the power 7 volt per meter. Okay, so that's the breakdown voltage for SiO2. So 3 times 10 to the power 7 volt per meter times D, right? And D, oh, the problem states, I forgot to say that. So the problem states that suppose we're working with a commercially available design and the smallest distance is 0.2 micrometers in that design. This is a commercial design. You would expect to see a separation of 0.2 micrometers in a commercial design. So what is the maximum allowable operational voltage with that design? Well, it's going to be 3 times 10 to the power 7 volt per meter times 0.2 times 10 to the power minus 6 meter, that's 0.2 millimeters. Meter goes with meter. So that's going to be 0.6 times 7 minus 6, 10, that equals 6 volts. This would be the maximum operational voltage for such a design. This is one example. The second example that talks about that's in the domain of dielectric strength, right, is example 4.17. We'll go about it quickly. Example 4.17. Right. And this example is about a particular application in cars, which is the spark plug. What's a spark plug? A spark plug is a device that kind of looks like this. Let's see. It has some conductor coming out here, and then it has another conductor connected to the body of the spark plug. Let me draw the conductors. Let me draw so this is the ceramic of the spark plug, right? And then the conducting part I'll draw in blue. So this has like a part here that hooks into the car, into the chassis, and then we have a pin here. So this, and then we have a pin coming out like this. So this part is at the potential of the engine block, connected to the engine block. And this part is the part where there's some circuitry inside the spark plug. This is the part that generates a large voltage, right? Some large voltage at maybe 10 kilovolt peak or 15 kilovolts, something large, right? The idea is that you want to cause a spark, and this spark is going to ignite the gasoline that's being sprayed inside the chamber, right? And get the engine. Once you ignite the gasoline, it explodes internally, and then it pushes the pistons, and the thing keeps running, right? The goal now is to generate the spark. How would you generate the spark? What is needed to generate the spark? So assuming this is air, right? What you need to generate the spark is to break down the air, right? That's what a spark is. It's plasma. It's like the nucleus and the electrons in the air. They break apart and we get a plasma, right? It's a breakdown mechanism. And we remember that for air, the dielectric strength is 3 times 10 to the power 6 volt per meter. Okay. So this tells me how much electric field do I need in here to break down the air and cause a spark. Right? Typically the distance between this distance is 1 millimeter. Right? So how do I turn this into millimeters? So this is 10 to the power 6 volt per a millimeter is a meter is 1,000 millimeters, right? So I end up with 3 times, let me do it this way, it's 3,000 volts per millimeter. or 3 kilovolts per millimeter. So for a 1 millimeter length, it's enough to provide a voltage of 3 kilovolts, right? For air. So if I provide a voltage of 3 kilovolts across this 1 millimeter gap in the spark plug, I will get a spark. Right? This is not the end though. We are not trying to push a spark in air. We are trying to push a spark in gasoline. So there's a gasoline mix. So there's a gasoline mix with the air. So the breakdown voltage will probably be different, and it is different. 15 kilovolts per millimeter. So it's substantially larger than air, right? Air is 3 kilovolts per millimeter. With the gasoline mixture, we will need to get a higher electric field intensity, higher, to cause a spark to go into the gasoline, right? So yeah, that's the statement of the problem. The statement of the problem is that hey, I mean, we could end up with a situation where the spark, for some reason, let's say something is faulty in the circuit and it gives us 10 kilovolt per millimeter, right? So this thing, spark plug, is designed to give us, let's say, 20 kilovolt per millimeter, but because of some fault in the spark plug, it only gives us 10 kilovolt per millimeter. But then when we go to test this spark plug, we put it in the tester and whatnot, we would still see a spark. Why? Because we are testing it in air, right? Because 10 kilovolt per millimeter is way beyond 3 kilovolt per millimeter for air. So it will work in air, but when it tries to work in an actual environment when there's a gasoline mist, the 10 kilovolt per millimeter is not enough to break down the gas mixture. So what is the solution in this case? The solution would be, let's say you have such a faulty spark plug. One solution would be to just take this wire and try to bend it closer so that the distance is less than 1 millimeter. Right? And that's the example. So in this example, they ask you, hey, if the circuit is only capable of providing 10 kilovolts, right? So E, for example, E is V by D, right? So if the circuit is able, and we know what E breakdown is. E breakdown is 15 kilovolts, right, per millimeter. That's electric field intensity required to break down the gasoline mixture, right? So what should the distance be if the voltage is actually not 20 kilovolt per millimeter, but it's faulty, it's only 10 kilovolts per millimeter? What should the new distance be? And you just simply solve for this. You get D equals V over E break, right? V is 10 kilovolts, what my spark plug is capable of giving me, divided by 15 kilovolts per millimeter. This goes with this, and I end up with 10 over 15, which is 0.667 millimeters. So if I have such a faulty spark plug, one solution is to bend the clip of the spark plug such that the distance between it and the tip of the spark plug goes from 1 millimeter to 0.667 millimeter, and that will solve my problem. All right. Let's do now example 4.18, right? And this is an example of refraction, the topic of refraction. All right. So what does example states? The example says that a uniform electric field intensity of magnitude 1000 volts per meter. So we have First, this is an electric field intensity in water. So we have water, a body of water, right? And then we have the air. And there's an electric field intensity at a certain angle, EW, and the magnitude of EW is 1000 volts per meter. Right. So this has a normal component, ENW, and then it has a tangential component, ETW. And then the permittivity of water is 80 times the permittivity of air. That means that the relative permittivity of water is 80. So epsilon R of water is 80. Okay. So let's call this theta W. Right? And then the field, when it leaves the water, it changes angle. So this is air, EA. And again, this will have an ETA tangential component and an ENA. Right? And then this is theta A. The question is, of course, air has a permittivity of epsilon naught, and water has a permittivity of 80 epsilon naught. So now the question is, what is theta A? Given that we know the magnitude of the field in water, and then we know theta W. Right, so the problem states with theta W is 30 degrees. Alright, so we can easily solve this. We can find the tangential and components of the field, right, and normal components. So the tangential components are just E. So this is E, I'll call this E. Sine, is it sine or cosine? Yeah, it's sine theta W, so E sine 30, which turns out to be 1000 times sine 30, which turns out to be 500 volt per meter, right? And then E, the normal component is E cosine theta W, so it's 1000 cosine 30 degrees, turns out to be 866 volts per meter. Right? So once we found the ETW, we know what ET is in air, right? It should be the same as ETW. The tangential component of the field in air is the same as the tangential component of W. We've established that. So that should be 500 volts per meter. Right? And what about the another assumption in this problem is that there is no charge density. Rho s is 0. At the surface of the water, there is no charge density. Right? So what about finding the normal component? Well, we know that d in water equals dn in water equals dn in air equals dn in water. Right? What is dn in air? That's epsilon naught E in air, EA, ENA, normal component in air, right, equals 80 epsilon naught. This is the permittivity of the water, epsilon W, right, EN in water. And we know what EN in water is. It's this value, right? So epsilon cancels with epsilon, so we end up with EN of air equals 80 En of W. Normal component in the water is 866, right? 80 times 866. That's it. So it is 69,280 volt per meter. So we have found both the tangential component of the electric field intensity in the air and the normal component. The magnitude of the field in the air is just using Pythagoras law, right? So this is EA and it has its two components. So we just added them up using the Pythagoras law. So ETA squared plus ENA squared, that's 500 squared plus 69,280 squared, square root. I mean, this is clearly a huge number plus a smaller number, so that whatever number we get is going to be close to 69,000. Turns out to be 69, slightly larger than 69,000 actually, because although 500 is small, it's, you know, it's not zero. So 69, small compared to 69,000, I mean. I don't mean it's small absolutely. All right, so the result is 69,281 volt per meter. What about the angle? The angle, we can find it by calculating the tan of theta 1, or not theta 1, theta A, theta air. So this is the angle. The tan is going to be ET, the tangential component, over the normal component. So that's going to be ETA over ENA. That's going to be 500 over all right, over 69,280. There's a small error in the book. It says 69,281, which is incorrect. If you want to do the tan is always going to be the tangent component over the normal component. It's just a regular triangle, right? And we've already calculated the tangent component in the air and the normal component in the air. Right? But anyway, the difference is just 1, so it won't matter much. So this gives me 7.21 times 10 to the minus 3, and I do the tan inverse. That gives me that theta A is 0.413 degrees. So although the field degree of incidence is 30 degrees, the field as it leaves the water and goes into the air has an angle of only 0.413 degrees. That is from the normal. That is refraction. All right, and this is the example. Okay, this includes recitation for today. Next on the next recitation class, I'll try to solve some more problems on materials, right? And then by then we would have covered the concepts of capacitance and energy in the electrostatic field, right? And then I plan also to ramp up again with the homework. So I want to get like at least before the end of the semester 4 more homeworks going on. It was kind of like a bit easy recently to just give everyone, you know, including myself, I'll admit, time to adjust to the, you know, crazy things that are happening around us. We are definitely living in interesting times. All right, guys. So looking forward to the next recitation. And as I said, we're gonna, by next recitation, hopefully you'll be finished with chapter 4, and then I wanna switch to magnetostatics after that. Right? I think we we would have, after the end of chapter 4, we would have gained a solid understanding of electrostatics, and it would be time for us to jump to magnetostatics. All right, thank you guys. See you at the next recitation.